right at the end of the last lecture, I started to explain what happens when you treat butadiene with HBr, and I pointed out to you that if you do it at a low temperature, you get mainly something called the 1,2 addition product, and the numbers 1 and 2 have nothing to do with numbering the chain. A 1,2 addition product is just an addition product that occurs on adjacent carbons. So you get mainly the 1,2 addition product, and you get some of the 1,4 addition product. And again, 1,4 just tells you that the carbons are 4 away, 1, 2, 3, 4. But if you do the reaction at a low temperature, then you get mainly, if you do it at low temperature, you get mainly the 1, 2. If you do it at a high temperature, you get mainly the 1, 4. So what is going on here? What is going on is that in the initial step, a terminal carbon is being protonated, and you get a resonance stabilized carbocation, and that resonance stabilized carbocation is then captured by bromide ion. If the bromide ion captures this resonance form, you'll get the 1,2 product. If it captures, that's fun. What am I doing here? I'm sorry, I wrote up something that's a bit silly. It should be that, and it should be that, and it should be that. Now we're okay. I'm just getting ahead of myself. Now we're okay. I got the numbers wrong as well. That's not good. Let's start again. At a low temperature, we get this, and in fact it's 80%. It's 80% and 20% here. And at a high temperature, it's 20% and 80%. I got that right. What's happening is that one end of the double bond is protonated, and obviously it's going to be the terminal end. The reason being that here you get a resonance stabilized carbocation, it's also secondary, whereas if you picked up the proton this way, you get a primary carbocation, and it's not resonance stabilized. So it loses out on 2 counts because the primary carbocation is less stable than the secondary one. So this is the direction of protonation, and now when this is captured, you get the 1,2 adduct. In other words, you get this, and you added something at that carbon and at that carbon, so they're all adjacent carbons. But if this one is captured by bromide ion, you then get the 1,4 adduct. You've added something here and something there. At this end, you've added the proton, at that end, you've added the bromine. So you get 2 adducts. Now, at a low temperature, it turns out that this reaction is essentially irreversible, and that this step is faster than that step. And consequently, the majority of the product is this. At a high temperature, however, the reaction is reversible. So if you get either of the 2 products, they lose HBr. Why should they lose HBr? Well, if this bromine comes out as bromide, it gives you a resonance stabilized carbocation. If this bromine comes out as bromide, it gives you a resonance stabilized carbocation. And that carbocation in both cases can lose a proton. So from this one, we could lose a proton from the end, get back there. From this one, we could lose a proton from here and get back again to butadiene. So at a high temperature, it's reversible. Now it turns out that this product is more stable than that product. And so when the reaction is reversible, what happens is that the more stable product accumulates. And so this is a case which is a very common occurrence where the more stable product is actually formed more slowly than the less stable product. Now that's actually quite complicated. You've got a reaction that at a high temperature is reversible. And this reaction can follow two pathways. One pathway is faster than the other, and it leads to the less stable product. When you have such a situation, the reaction is reversible. So if you form some of the less stable product, it can go back to starting materials. If you form some of the more stable product, it can also go back to starting materials. Under those conditions, eventually, the more stable product will accumulate and be the major or exclusive product. If you do this same reaction under conditions in which it is essentially irreversible, and in this case it just means lowering the temperature, then again you'll get two products, but the less stable product is formed more quickly. Now we're not going to go into the details of why one of the products is more stable than the other, and why one of the carbocations is captured more rapidly than the other one. That's well beyond this course, and it's not so easy to give a complete answer. But it's a phenomenon that you need to know about. You have a reversible reaction, gives two products, they're not going to be of equal stability. Under appropriate conditions where reversibility is easy, the more stable product accumulates and is the major or even the exclusive product. Under other conditions, the faster forming product, which is frequently the less stable product, is the one that's formed and is the majority of what you get. Now, what you should do is to try problem number 13.10, which is the same in both textbooks. I now want to go on to another reaction of butadiene. It's a very famous reaction, and it's called the Diels-Alder reaction. Diels was a German professor, and Alder was his student, and they discovered a reaction that makes six-membered rings. And I want to tell you about this reaction because it's extremely useful and has been used thousands of times, and it's also very important, and Diels and Alder were awarded the Nobel Prize for discovering this process. Well, actually, I shouldn't say for discovering it, because they weren't the first, but they were the first people to advertise it and realise how important it was, and they were the first people who studied it. The previous people had done the same sort of reaction, but hadn't realised exactly what was going on. Now, a very typical example of the Diels-Alder reaction. Well, let me first give you the very simplest possible example. If you take a diene and an ene and you heat them, what happens is a process summarized by those arrows occurs, and you get a six-membered ring containing a double bond. Now this ene is called a dienophile, this part, of course, is called a diene. So you take a diene and a dienophile. Now a diene, obviously, is a substance got two double bonds in it, and they have to be conjugated. That's why we're dealing with this in the chapter of conjugated systems. The dienophile is, what does that word mean? Well, a bibliophile likes books, a francophile likes France, an anglophile likes England. A dienophile likes double bonds. And so it's a substance that likes double bonds. Now it turns out that that is the very simplest example of the Diels-Alder reaction, and that simplest example doesn't work very well. You have to heat the guts out of it, you have to really heat it up, and the yield is lousy. But there are hundreds, maybe thousands of Diels-Alder reactions that work beautifully. And it turns out that if one of the components, at least one of the components, the dienophile, has electron withdrawing groups on it, then the reaction works nicely. And if the diene has electron donating groups on it, that also helps the reaction. And if the diene has electron donating groups and the dienophile has electron withdrawing groups, then it's a beautiful marriage and the reaction works great. So let me show you another very simple example, which probably you will do in the lab if you haven't already done it. If you take butadiene and maleic anhydride, I will write these three curly arrows again, and you can see that again I generate a six-membered ring that has one double bond in it. And I should tell you that very often, just like the starting materials are described as diene and dienophile, and here the maleic anhydride is the dienophile, just like those two have special names, the product sometimes also is given a special name, and it's called the adduct, or the Diels-Alder adduct. Now, things are not as simple as this equation would indicate. And there's a reason, well, this isn't the reason why it's not simple. Just let me say that there are some factors that you need to take into account. I'm going to draw up another example to illustrate these various factors. So what I'm going to do is to take this compound and this one, do the Diels-Alder reaction, and this now illustrates some of the factors. You'll notice that in this compound I have a Z geometry. That double bond has the Z geometry, because at this end there are two substituents, hydrogen and the ester. Of those two, the ester is the higher ranking. At this end there are two substituents, hydrogen and an ester. Ester's higher ranking, so at each end of the double bond the higher ranking groups are on the same side. So it's a Z. And you'll notice that in this adduct, I can even emphasize it by writing in the hydrogens, in the adduct Those two ester groups are again on the same side, but because it's in a ring, we now say that they're cis. So what has happened is the geometry of the dienophile has been preserved. And if, for example, I were to do very similar experiment, but use the E isomer of the dienophile oops, we don't want to do that. I've made one mistake already in this lecture and I don't want to make a second. If we use the E isomer of the dienophile, then the product has the two ester groups on opposite sides of the six-membered ring. We say we get the trans isomer. So there's something about this Diels-Alder reaction that tells you that the geometry of the dienophile is preserved. That means if you want a six-membered ring with two groups that are going to come from the dienophile to be on the same side, you better use a dienophile that has those two groups on the same side to begin with. If you want the two groups in the product, in the adduct, to be on opposite sides, then your dienophile must have them on opposite sides. So that's a very important point about the Diels-Alder reaction, because you know two things. If you want a particular structure, you know which geometry for the dienophile to use. That's one thing. The other thing is, since there's a direct relation between the geometry of the dienophile and the geometry in the product, you know that this is a jolly good reaction because there isn't scrambling. If you had a mess, both cis and trans in the product, irrespective of what you started with, it wouldn't be very useful. A useful reaction is one that gives you control, predictable control, over the stereochemical outcome. Because if it doesn't, then you've got no control, you're going to get a mixture. And when you do an experiment, you don't want a mixture, you want a single pure product. So that's one complication, or not a complication, it's a beneficial, a very useful aspect. But there's something else that's hidden in these pictures, because what I haven't done here, I haven't got any substituents on these two carbons. And clearly I could have, say, a substituent pointing this way, or it could be pointing that way. And at this end I could have a substituent pointing that way, or it could be pointing that way. So this double bond could be a Z or E double bond, and this one could be a Z or E double bond. And what's the story? In other words, I told you that the geometry of the dienophile is preserved. If the dienophile has two groups cis, they end up, or the Z, they end up cis. If it has two groups E, they end up trans. What's the story with respect to the double bonds of the diene? Well, it's not very difficult for you because the story's the same. In other words, the geometry of the double bonds in the diene is preserved. But it's actually a heck of a lot more difficult to draw the pictures that show that than it is to draw the pictures that show the geometry in the dienophile is preserved. As you'll see in a moment. There's another complicating factor. You notice that I drew these nice little curly arrows. They're a British invention, invented by Sir Robert Robinson, professor of chemistry, who was a professor of chemistry at Oxford University. You notice that I've drawn those arrows, and what these pictures mean is that the geometry of the diene must be what I described to you in a previous lecture as S-cis. You see, a diene could be like that. That's the S-trans conformation of the diene. But if you do that, there is no way in which this could reach that and that could reach that. So the geometry of the diene has to be S-cis. The diene has to be able to reach an S-cis conformation. Therefore, if you have, to give you a sort of semi-example, if you have that diene, it won't undergo a Diels-Alder reaction. You can wait from now till Christmas and mix it with maleic anhydride, nothing will happen. Because the geometry of the diene is wrong. The two ends cannot simultaneously approach the two ends of the dienophile. On the other hand, if you take an isomer of that, and you mix this with maleic anhydride, it'll react. Because the two ends, you see the diene part has the S-cis conformation. And so this end and that end can simultaneously approach the ends of the dienophile. So there are several things that I've told you. The diene must be able to attain an S-cis conformation. The geometry of the double bonds in the diene is preserved, but I haven't yet shown you any examples. The dienophile, its geometry is preserved, and I've given you a couple of examples. What I need to do now is to give you examples of the geometry of the diene being preserved. And you remember a moment ago I said that's more difficult to draw than preservation of the geometry of the dienophile. So I'm going to clean the board and then I will draw it.
I hope no one knows me. No one knows. Oh, I did that to you, huh? What he doesn't know won't hurt him. Just wait. YouTube's a big place.
Here is the reaction that I'm going to talk about. Cyclopentadiene, that's this baby on the left. Cyclopentadiene and maleic anhydride. And what I've done is I've drawn the three Robert Robinson curly arrows, and I've shown you the product. But I haven't shown you the stereochemistry of the product. I've just shown you the basic carbon framework. And so now what I've got to do is to redraw the two starting materials next to one another in exactly the way in which they actually approach one another. And if I do that, you will then be able to see what the shape and the stereochemistry of the product is. And you will notice certain things about it. So let me see if I can draw the shape very, very nicely. What I'm going to do first I'm going to draw the cyclopentadiene. Let me put in the hydrogens. There they are. And underneath it, now you can see this diagram is a heck of a lot more complicated than anything else that I drew up today. What I'm doing is I've got the cyclopentadiene and I'm holding it like this, and I'm holding the maleic anhydride such that, let's get some different colours here, such that the orbitals in the double bond of maleic anhydride are overlapping with the p orbitals at the ends of the diene. And what's more, the rest of the maleic anhydride molecule is underneath the cyclopentadiene. So let me just draw what happens if it's not underneath. See, in this one, the carbonyls and the oxygen are pointing that way, but in this one, the carbonyls and the oxygen are pointing underneath the rest of the diene system. So the situation is really very much like this. If this is the diene, and this is the dienophile, and my hand is the double bond of the dienophile, it could be like that, or it could be like that. If it's like this, then the carbonyls and the oxygen are pointing away from the rest of the diene. But if it's like this, the carbonyls and the oxygen are pointing underneath the rest of the diene. So there are two orientations, and one of them is favoured. The one that's favoured is this one. And it's favoured because of what are called, I'll write it down, secondary orbital interactions. Now that's a big name, big bunch of words. It's very easy to understand what it is because these orbitals here in the central part of the diene can clearly interact with the B orbitals of the unsaturated groups on the dienophile because you see they're over one another. Whereas here, these babies in that region cannot possibly overlap with these because they're far apart. And so it's the secondary orbital interactions that favour this one. Now if that is the case, then if you follow through with the curly arrows, you can easily see what the shape and stereochemistry of the product will be. And what I'll do to make that easy for you is I will simply redraw this picture without without the p orbitals, so you can see everything clearly. So I'm going to do that, and then, yeah, that doesn't help you. That's too messy, so let's try it again. And that is equivalent to, it's easier to actually draw it like this. So that's the product. So you notice a few things about that product. One of the things you notice is that this CH2 group is pointing to the opposite side of the molecule than the carbonyl groups. And the reason for that stereochemistry is because this is the preferred direction in which the two components approach one another. And this is given a name. It's called an endo transition state. In a 2-2-1 bicyclic system, which this is, things that are pointing upwards are exo, and things that are pointing downwards are endo. That's just a naming system. So, let me just, this is getting quite complicated, so let me just recap what I've told you. I've told you what the Diels-Alder reaction is. The very simplest example, it doesn't work very well experimentally, is to heat butadiene and ethylene. You get a 6-member ring containing a double bond. These reactions go much better if the diene contains electron-donating groups, and especially they go better if the dienophile contains electron withdrawing groups. And if both, if the dienophile has electron withdrawing and diene has electron donating, it goes even best of all. The diene and dienophile approach one another in a particular way via what is called an endo transition state. And the reason why they approach one another preferentially in that way is because of what are called secondary orbital overlap. The other thing I told you is that the geometry of the dienophile is preserved. So if you have two electron withdrawing substituents on the olefin that are Z, they'll end up cis in a 6-membered ring. If they're E, they'll end up trans in a 6-membered ring. I also told you, but did not give an example, that the geometry of the double bonds on the diene is also preserved. And I will now show you an example of that. And that diagram is also quite difficult to draw. But these things become very easy to understand if you build a model of the two bits and hold them in the correct way in which they approach one another. So I will clean the board and I will then show you why or how the geometry on the diene double bonds is also preserved. Now you'll notice in this reaction that you form two single bonds, there they are, and you also generate 1, 2, 3, 4 carbons that are attached to 4 different things in the general case. And so there are at least four stereochemical questions to answer, because you want to know what's the stereochemistry here, what's the stereochemistry there, what's it there, what's it there. And I told you that here and here, which comes from the dienophile, you can predict because the geometry of the dienophile is preserved. And I've also told you that the approach of the dienophile and the diene follows the endo approach. So you can work out stereochemistry there and there. But I haven't told you how to work out stereochemistry in the other places, so let me do that now. Yeah, sure, no problem. I'll draw it again here.
Maybe I'll change this one. Since I have so many. There we go. His drawings look a lot better than my drawings. I messed up.
Okay, if you have substituents on these carbons in a 2-to-1 bicyclic system, those, such as this one, that are on the same side as that point, are described as being exo. And those that are on the opposite side to that point are described as being endo. So the exo face is this top face, and the endo face is the bottom. Now I want to show you the stereochemical outcome when you have substituents on the diene. And as I said, that is not so easy to draw, but it's much easier to see if you build models. So let's take here I've got, obviously, this compound. Both double bonds have the E geometry. And what I'm going to do is I'm going to put underneath this a dienophile. And I'm going to put the very simplest dienophile, so that the diagram doesn't become too complicated. I'm just going to put ethylene. And now, I'm going to do that diagram, and what you will get which is equivalent to, have I got that right? Yes, I must have it right. Now, I'm sure from this diagram you can understand that that's what I get. What some of you may have a bit of difficulty in understanding is how this picture actually correlates to that. But you can, well, you just have to build a model. And if you build a model, hold it in your hands, you will see that these two pictures here on the right are identical. Some of you will be foxed by this when you look at it on the screen, because this is pointing towards you, this is pointing away from you, and yet in the product they're both pointing away from you. You have to imagine that this is opened out, and if you open it out, this hydrogen which is pointing towards you will stay pointing towards you, but this hydrogen which is in this picture appears to be behind the board will actually come to the front. And the only way to really understand that is to build a model. So you now know a number of things about the Niels-Alder reaction. And what I'd like you to do is the following homework questions, which are 13.11, which is the same as 13.12 in the 9th edition. And you should do 13.12, which is 13.13 in the 9th edition. Then you should do 13.13. Oops. There's cleaner. And 13.14. .15, which is 13.16 in the 9th, and 13.17, which is, 13.16 in the 9th, in the 10th, which is 13.17 in the 9th, and I have 3 more. It's not a lot of work. I mean, it's coming to the end of the week and there are no good movies on, so I've got nothing else to do.
What are the classes that we have? That's nuts. Are we doing 1318? Are we doing 1318 at all? I guess not.
If you do those, you will have a very good understanding of the Niels-Alder reaction. And the only things to remember about it are that you need a diene and a dienophile. The dienophile should preferably have electron withdrawing substituents, 1 or 2. The geometry of the dienophile is preserved, and the geometry of the diene, the substituents of the diene, is also preserved in the product. Yes, you have to keep quiet so that I can hear.
How can they both be back?
No. This is what I was explaining before. I said that this stereochemistry is correct. There's no question about it from the stereochemistry of the diene. And I said that you will likely find it difficult to take this geometry and untwist it and get this, because here the methyl is pointing towards you. And here the methyl is pointing away from you, and yet in this picture they're both pointing away from you. And the only way to understand that that is correct, I admit that it's not easy to see. The only way to understand is to build a model. And if you build a model that looks like this, and just twiddle it around a bit, you'll see it actually is that. Okay, that's enough about conjugated systems, and in the last 5 minutes what I need to talk about is aromatic compounds.
Where are you going?
No, I'm just finding myself alone. I've decided to stop writing.
I'm sorry. I think it's the same happened in the 90s.
Oh.
Oh,
Are you going to Cab
yeah, there's
Basement?
some mistake. I'll fix it up next
Yeah.
lecture.
We have a meeting today. You already said that, right?
It's 13.13 in the 10th and 13.14 in the 10th. And I don't know what it is in the 9th, but I suspect it's the same number. Okay, I need to start talking about aromatic compounds. Just let me increase the volume so that I can overcome the chattering. I need to talk about aromatic compounds, and first of all you'll need to know why they're called aromatic. It turns out that in the early days of organic chemistry, a number of compounds were obtained from plants that had a pleasant smell. And some of these compounds were found to contain a particular subunit. Now, one of the compounds, I'll draw up the picture, but I'm not yet going to explain what this ring means. One of the compounds is obtained from almonds, and one of them, just as an example, is from cinnamon. So these things have nice smells, and it was found that many of these compounds have this piece in them, which I've written in two different ways, and consequently, because of the pleasant aroma of these compounds and the fact that they all had that piece in them, generally the trend developed to call compounds that had this piece in them aromatic compounds. So that's how the name arose. The next thing that you need to know is that the main compound in this series, the parent compound, is something called benzene. And benzene was obtained from a gum called gum benzoin, which was isolated from a tree that grows in Java. And if you take some gum benzoin, you can get from it a substance which is an acidic substance, which was called benzoic acid. You can see the relationship between something from a plant that's called gum benzoin, you get an acid, you call it benzoic acid. And benzoic acid was found to give the parent group that's present in all these aromatic compounds, and therefore it was called benzene, and that name was given to it by a person called Clive. Okay, I think that's it. Remember, this Friday there's no lecture, but we will have a makeup lecture, maybe two of them, so I'll arrange the dates